Good. Okay.
Okay. Morning. So this is another, you guys had our lessons that are kind of overview. Very picky with, and it's not that one. Again, all of the lectures are available to you. So if you feel like we're missing something, don't worry about it. We can access all of it. All right, so I'd like to just acknowledge that we're coming from a place of diversity, right? There's the diverse backgrounds of the instructors. We are coming from different institutions, different places in the country, born in different countries. we think differently about how we educate, and so lucky you get all that, right? We have a lot of different teaching styles, and I'm going to share with you some of my ideas of teaching styles, but every person end up here is, and some will really work for you, and some will be like that. But that's okay, because if you put someone else, you guys work together, they don't do that. You guys are all coming from, and your learning styles are all good. So we have to try to take all that information and put it all together to get you the best. Okay. So I want you to just consider your own learning style and just think for a moment. When you get to learn the way that enriches you the most, is it because you read the chapter? Is it because someone was speaking it to you in front of a classroom? Was it because you were discussing with your peers or with your instructors? Was it because someone put a graph up? But for me, it's that. It's a graph. So, is it an equation? You can look at that equation and immediately know, like, oh, I've got those terms, I got it. Is it because you are actually getting hands-on instrument, hands-on data, hands-on water? What is the way that speaks to you? And I will guarantee you that you will get a little bit of all of this, of course. But I encourage you to kind of broaden a little bit and try and get it in some other new places. Better scientists. So I'm going to employ a couple little things in this lecture, and these will be themes that go throughout the class. So one independent way of learning that we can use pedagogically is something called the knowledge survey. Has anyone ever taken the knowledge survey in class? You have? Yeah. But not all of you have, or maybe that term isn't new. So we have, I'm going to give you a knowledge survey, but essentially, what a knowledge survey is I ask you. I don't ask you to answer that. I ask you to tell me how confident you feel that you know the answer, right? Then we do some work, and then I give you that same knowledge survey again, and see whether your confidence in your understanding has improved. And it turns out the knowledge survey is actually a tremendous tool for assessing whether you have learned. You don't have to write everything out for me, and more importantly, have to read it, right? But your confidence. What it just demands is that you are really honest in your knowledge. No one else looks at it. You don't need to be like, your answer's like, I have no idea. You don't have to worry. No one's seeing that. But it's a little signal to yourself, like, wow, I should listen to this part, right? Okay. And one of the ways that we have for learning are these collaborative approaches. And so one is think, pair, share. And that's gotten a lot of like advertisement videos people start to recognize that pedagogy matters in learning. And so think, pair, share is the first step is to think. I give you a problem, or anyone else gives you a problem, and you think about it yourself. You brainstorm some ideas. This is what I'm talking about. This is how I would solve this problem. Then you pair up, and you discuss with each other your different strategies. You're like, oh, I thought about that. That's a really cool way to think about it. Then you come to a bit of a consensus as a pair, and then you share with broad class. Their strategies. And it's a way of like really solidifying your own knowledge, learning new ways of approaching problems, and being able to come to a broader consensus. Because you guys are going to be presenting your results of a lot of analyses as a giant group. It's important you guys figure out how to navigate this type of a problem. Okay. The other thing that we like to do is called jigsaw. And so that's where individuals or small groups work on an aspect of the problem. They get together, like one person, so you guys are all working on a problem. You guys are working on a different problem. Each table has a different problem. Then we split you up, so there's one member of each table in a group that we share. You don't get to do everything, but you get to learn everything, right? So this is what we'll be doing in lab. You guys will be working in groups, learning things, and then sharing across the labs. Very effective way of learning. And then finally, some assessments. So one of the, I didn't pull it out. I'll pull it out later. I brought sticky notes. This is the old slide. No, this is not good. I know, it says 2023. It's only that slide. Okay, it's only that slide. You are not giving it to Guillaume because he's not here. We're giving it to Charlotte and Patrick. If we are, somebody is presenting something up here, and you don't understand it, you write it on the screen. Some question or point of confusion, or you learn something in a lecture that you are so excited about, you just want to share it, write on a sticky note and give it to them. At the end of the day, we'll look at the sticky notes. If there's a point of confusion, we'll make sure we return it. Okay, or we'll work with people on it. Okay. All right. Okay. And then finally, the assessment is the daily presentations. That is where that's your accountability for the work of the day. And what happens is, do the work, we analyze the data from lab, you present it to us, we sit in the back of the room and we raise our hands, we're like, what the how does the data look like this? And then we see this. You want to rework it, think about those things. And you revise, and you resubmit, and we're like, aha, we got it. You're good. Okay. So these are the strategies that we're going to be using in class. Okay. So here's one. Yes.
Exactly, sticky notes. Remember several things. We don't understand something.
Yes.
Don't be don't feel bad about not understanding. The whole purpose here is to do. If you don't, there's a problem. And we're going to deal on lectures that if you understood it, tell it. So don't be shy. Each time is for you. I mean, for us, it comes at fun. Also for us. But most of the things is how, get the next generation, pass the knowledge to the next generation, build on it and develop it. So get that to us, don't be shy. Because anything that's really being gathered, you want to hear again or something. The point here is not to cover material. Covering, if you read the book, it's all covered there. It's to understand it, understand it sufficiently, the other body, or maybe find holes in it that nobody did because
And if you don't ask, you keep going. I say then you have any questions. Maybe correct it 5 seconds. Really long silence. If no one asks, I'm like, okay, we're good, so we're moving on. So you raise your hand, raise the hand. All right, so let's do a knowledge survey. So write down the radius transfer. Take a moment, think about it. And then in your mind, do you know just what to do? You get pretty close. Try. Try. You find The way you do it. It's the way it is. So in your mind, write down any of those. Write it down. Yeah, write it in mind. And we'll get back to it. So, you know, you can start off like this, and then we're going to spend some time. We're going to do a little bit with the radiation if you say. That's me. I'm most of on the phone here. And I did for a today. Pretty nice. And then after we work together, we're going to take it again. We're all going to be like, "Well, we crossed out and y'all did it." Get the radiation transfer equation in and out. That's our goal. All right. So the big pair share. So if I wasn't clear before, you guys should take one. Okay. So, oh no, that's the other one. Big pair share. 1 and 2. So I give you a problem, radiation transfer equation. Think about it. Wait. You have to really think about it. We'll often miss that first part, thinking yourself. Then I ask you guys to pair up, and I ask you guys to pair up. And I ask you. Okay? So you can sit on the problem on your own, you pair with a partner, you discuss the ideas with the group. And you come to a consensus, and that consensus part is important, or consensus with caveats. Right, that you want to think about. So what I love about this is that at the end of all of these exercises, you have a problem solved with all of the perspectives of the group. Everybody has contributed, everyone's contributed their ideas and thoughts. Learn something about the way other people do, which is really helpful. All right, the jigsaw. This is typical. This is and we have somebody give you guys a problem. I want you to solve a radiation transfer equation that's sketchy. I want you guys to write. I want you guys to be schematic. I want you guys to analyze the data. I want you guys to not post, right? For non. And we spend time doing that. And then one of you from each table get together and you make sure that you understand each other's way of thinking, that you can make all the different parts consistent and efficacy. And in doing so, each of you walks away with a little bit of all the colors. Have you tried one? All colors. Emmanuel, show your shoes. All colors. Everybody becomes an expert. Everyone has a little color. Here's the sticky notes. So this person, after hearing the first few lectures today, says, I didn't quite catch the difference between radiance and irradiance. I know you're going to talk about it later, Andrew, but I need to know it tonight before I start. Okay, so give that speech. And then the daily group presentations. You guys will all be standing up here in your room, literally giving presentations to us together. It's good to have someone standing next to you. All right, so let's do it. We are going to consider the radiation transfer equation, take a piece of paper or whatever writing you can write on. I want you to sketch a diagram, write an expression of the radiation transfer equation, but first take the knowledge survey. Get it. Go ahead and do a little bit if you want. Write down the whole thing. Idea, take literally a minute to think about how you think about the radiation transfer equation. You can translate the words. Radiated. Went back. Radiate quantity to the end of it. Perfect. All right. So we're going to move through this. We're going to sort of slowly start through the radiation transfer equation. Andrew showed you a beautiful painting by Ron Zenfeld. This is my grab an image off the internet version of that. A photograph of light coming from the surface heading into the water. So we're going to talk about how that light do it in a couple of different ways. We're gonna go in the forward direction. We're gonna go in the backward direction, the inverse direction, which Andrew talked about. So just so that we're all clear about forward or direct models, imagine that there's a dragon. How many people are Game of Thrones fans? Anyone? You read the books? Okay, so there's a dragon. And we know there's a dragon. And we're friends with Khaleesi. So we've seen that dragon. And so we know what the tracks are gonna look like because we have the dragon. And we know that this particular dragon has, you know, these beautiful claws and also has a tail. Did you know that that's actually dragons that have tails? That's different. Okay. So we can predict the tracks because we have the dragon. All right, the inverse model, which is a model, right? We had a question about inverse modeling, really modeling. There you go. Yes, model. All right, so we observe some tracks. And we see the claws, and we see the tail. Okay. And so from that, we determine what kind of dragon it is. Is it this dragon? Dragon I controller, or is it this one? Right. And so our uncertainty in what we've measured and projecting what we've measured in this inverse problem, hopefully we have less uncertainty between the cute baby dragon and the big giant. Hopefully we've narrowed it down in size based upon the charts. So inverse problems really need to get their uncertainties down. Okay, so optically we have forward and inverse models. And so if we think about starting with the inherent optical properties of sort of scattering, that's like measuring dragon, we can predict what the light field is, right? So we go between the inherent optical properties, which we've spent the entire week on this week. We're going to relate those to the radiometric variables, measured light. We're going to be spending on next week, mostly on radiometry. And so if we know those inherent properties, we can estimate what the radiometric variables are, and we do that via the radiative transfer equation. The radiative transfer equation allows us to take our measurements of absorption and scattering and predict what the light is going to look like. So we use hyperlight in this class. In the inverse model, we can also relate that to apparent optical. So in the inverse model, we can either measure the apparent properties or the radiometric variables, and via an inverse model, predict the IPs. So we can measure an apparent optical property from a satellite, and we can then say what the absorption and scattering were in the ocean, which for people who are interested in biochemistry allows us to say how many phytons are in the water, what species of phytons are in the water, how many color dissolved or organic matter is in the water, how much spin particles, what size are they, right? So that's where the power of the inverse model comes in. So today, I'm just going to review it. We're going to spend a lot more time with the radiative transfer equation. But I want to start with the source. So, I love this image. This is from the space station. Looking at the sun, horizon. And my question to you is, let's make some observations about the source. Can you tell me about the sun, just from this image? Yeah. It looks white. Okay. Because you have color. What else? I know you're dying to say something, so just say it. Yeah, it's really bright. So it looks like there's lots of energy. all directions down here. So it's emanating in all directions. Equally? There's some dark and light patterns to that emanation, right? So, is that the sun or is that our measurement? We have to find out, right? We don't know. But these are some observations. Okay. So, black body radiation, you probably remember this in physics, maybe high school, maybe college. But remember that any object that has a temperature above absolute zero is going to emit electromagnetic radiation. We emit electromagnetic radiation. The big emitters of microwave, we are. Not enough to cook an egg, but you know, still, depending on how warm you are. So this is the Planck's law equation. So Planck's law is the spectrum of emission that a body with a temperature is going to emit. And it's complex. It's not a warm and fuzzy equation. There's wavelength and there's Planck's constant, speed of light, all these different terms. But it's the emission, the amount of energy and the wavelength as a function of temperature. And so other people have worked with this type of these observations and have figured out that the hotter the object is, the more it emits. Right? So that really brightness of the sun is because it's really hot. It's making a lot of power. And it turns out that it's related to the temperature, but power. So you know, a little bit warmer is a lot brighter, that form of power. And then Wein's displacement law tells us that the hotter it is, the shorter this way, the shorter the wavelength is of its maximum. So here's the lambda max for this very warm object, 75 degrees. And I would just note, I teach in a department of oceanographic science, so I'm with a bunch of geologists. And it turns out that the core of the Earth is about 7,500 degrees. So when you look at a geology textbook and it shows the core being red, it shows that it's hot and molten, it's actually blue. If you see it. So as the object gets colder, it will emit at a longer wave. So the sun's about 5,700. So it is maximal in the. That's this right here about. All right. So that's the emission, but it said it was white. And does that look white to you? It's like there's a lot of colors in there. But this is the spectrum over which the visible of which we can see. So if we put that on a scale, it looks like this. So this is blue. I'm clever, I can change. This is blue, this end. This is red at this end. And so if we highlight this, what would the perfect light spectrum look like? Right? It would be flat. That's not bad. It's pretty flat, right? But yeah, the sun's white. Don't look at the sun. Don't check me out on that. Not saying I haven't looked at the sun. It's just don't do it. Mind you for yourself. Verify that it's white. You can measure it. Okay. So those are all the colors. It's pretty white. All right. So then we get to the atmosphere. Love this picture of the atmosphere. Make some observations. What do you see about the atmosphere? Yeah. It's thin. Yeah. Weird. What makes you say that? Yeah, it's not random. It's gradient, right? That's different, say it's a bunch of different colors, but it's a gradient color. This one. Oh, you sort of raised your hand. Right? It's sort of white. Blue. Everywhere? It changes. Yeah. And this is what the sun, right? So it changes. Relative to the sun. I have to repeat what I write that. Sorry about that. So it changes. Well, I mean, so it's actually quite red by the sun. Right? This is sort of reddish here. Is that coming from the atmosphere? We have a lot of questions about this speech. One thing I want you to walk away with is the fact that it is so thin. Right? And it's our barrier. Don't screw it up. Right? We should be screwing up. Very good. We shouldn't be messing with it. It's all that's protecting us from space. Okay. We made some observations. All right. Optically, when we look at the sun, does the sun look really different from the top of the atmosphere to Earth's surface? So the top figure is above the atmosphere. This one is from the ground. How different does the sun look? This is the sun. Still white, still bright, and still emanating all directions. Right? What about the sky? Really? Right? We go from the black sky of space to the blue sky that we know and love except today. Okay, now we're in the ocean. What's different about the sun? The white. It's still pretty white. Still emanating in all directions. It's less than dark white colors, but it's definitely blurry. Right? There's a blurriness. So something is changing, right? And the sky is sky, right? We're seeing really, really different colors. So, you know, sort of looking at our source depends upon where we're measuring our source. So when we get out in the lab next week, we're actually measuring irradiance or radiance. It makes a difference. We're not going to be able to send you out into space, sorry. But we are going to be able to make measurements at the surface and measurements in the ocean. And we are going to be able to separate, you can separate out the light coming from the sky, skylight, from the solar beam. And see if they actually in fact are different colors. I think they are. Maybe do something like that. All right, so here's the spectrum from those three. So this is the spectrum of the source at the top of the atmosphere, at the surface of the Earth, and 10 meters below the ocean. Okay. So at the top of the atmosphere, it's different from the curve that Planck would predict. The Planck curve would have been like really nice and smooth. Really nice and smooth, right? And we see these lines. And your first thought might be like, oh, it's a noise sensor. That's a pretty good thing to think about. And then you might think, but what if it wasn't? What if I measured the same thing with many different sensors? You're like, oh, there's a signal there. A noise, one person's noise is another person's signal. So if you happen to be interested in the absorption by gases in the photosphere, which is the sun's atmosphere, you would be very interested in that noise, because those are very defined spectral bands that tell you the gas concentration of the photosphere. And to us, we're like, oh, gosh, can we just put a smoothing function on that? So remember that every time you make a measurement and you see something that you might think of as noise, check to make sure it's not a signal. Because every time you hear something like that, it becomes an opportunity to learn something new. So challenges or sources of variability, or things that you're trying to remove so you get to the signal you want, that's an opportunity to learn something else. So measuring the solar spectrum at the top of the atmosphere allows you to learn something about the sun. Okay? Then we get to Earth's surface and we see these other features here, 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 and the fact that we've lost all this amount of energy. That's the related to all optical properties of the atmosphere and the absorption of gases, scattering by particles, and loss of energy. So there's a lot going on in the atmosphere. Learn a lot about the atmosphere by comparing those two. And then finally, we get to beneath the ocean surface, and wow, have we lost a lot. Right? Water absorbs tremendous amounts of energy. And then we also see some losses in other parts of the spectrum due to all the constituents of water. So just by thinking about measuring the radiance from the sun at these different levels in the ocean, we can infer a lot about the sun, the atmosphere, and the ocean. All right, so the atoms of the atmosphere, what color is the sun? White. Color is the sky? Yes, the inner distribution of light that we might see on this ocean, given that sun, remembering that the sun doesn't go so far away. Give it a try. Well, next guy, it would be fun. Here. There was no atmosphere. It would look like the measurements in the space station. No atmosphere. That's important to know because sometimes when you read some of the old modeling papers, they ignore the sky. It's easier. Make sure. Okay. The distribution of sunlight. Beam of light. Sun is at some angle. But because it's so far away, the lines are coming in parallel to Earth. Okay, at this distance, whatever angle the sun is at, it strikes the Earth parallel. I've taken away the atmosphere. There's no atmosphere. You are so good. So this, if you're going to start modeling, start here. And in fact, I would start with the sun directly overhead and didn't really angles. Right? As soon as you have an atmosphere, you have to change the spectrum because of absorption by gases. We have to change the angular distribution because of skylight and aerosol scattering, all those things. But this is what the solar beam would look like. Then you have to add all of the other light incidents, and it gets complicated. So start here and then add things in, right? I mean, unless you just put it in your head. But it's really good to start with the most basic before you jump right in. So now we add the atmosphere, color of the sun, white. It's a little bit red shifted, but not enough that I can change the color on the sun. The sky is now blue. because of the scattering of the blue photons out of the solar beam by small particles, by gas. Okay, so on my screen, I just turned my sky blue, it can show up on the big screen. And so then we end up having our solar beam, but then we also have light coming in at all angles from the skylight everywhere. Should be straight lines. All right. So we can make some conclusions based on just these observations that the atmosphere reduces the intensity of the sun, it changes its color, it changes the illumination. And so in some of the radiometric properties labs, we're going to look at the variations in solar radiation. If the sun comes out, we're going to compare the color of that solar beam versus skylight and look at the angular distributions of solar radiation. Very simple, like paper towel to only look at one portion of the sky. Okay, so we're at the ocean surface. And I want to talk a little bit about surface effects. And again, we'll talk about this more later about some of the processes. So we have this incident beam. What happens to that sunlight once it reaches that interface between the air and the ocean? It changes direction. Which way does it go? Perfect, goes back. And part of it actually gets reflected, right? Reflection. There's reflected beam, so there's reflection, which is not reflectance. Reflectance is something else, it's reflection. And then what else happens? Okay, it goes in the water. First, get in there, get across the interface, and it does change direction, right? We can talk about later all the laws that will tell you about that. Okay, so we have an incident beam, a reflected beam, and a transmitted beam. There might be some light coming back out of the ocean, then we can start to talk about reflectance because it contains all the properties of water once it comes out. But it's different. This light coming out is not the same. It's not equal to light that's reflected off the surface. So it contains a lot of information. But there are very different processes that give rise to them. All right. So here's a really beautiful image from space that I got from the NASA Image of the Day website, which is this is Bowdoin, India. So it's in the Indian Ocean. It's an atoll. So what you're looking at is the lagoon. That red dark ring around the outside is the actual atoll, and then the ocean outside of that. And the weirdness of this image is simply caused by sun, which is that reflection off the surface. Powers of reflection. If you look at this from the side view, you don't have wind. It looks very different, right? You can see the atoll, you can see the interior waters, which are brighter than the waters on the outside. And so glint can be not effect. I think there must be some clouds too, but why are the clouds not over the atoll, right? That would be confusing to me. Atoll doesn't sit up and block the clouds. Crazy, right? I've never been there. I would love to go. All right. So the light goes to depth. What happens? We said, right? Then we go. And right. I'm going to try to do this. Yeah. Okay. So absorption is going to remove light. This removes the energy. That energy goes into some other compound, either within a particle or dissolved. What other things can happen besides absorption? Scattering. Scattering doesn't remove photons, it just redirects them. And we can also have re-emission, like things like fluorescence, where, say, the chlorophyll molecule inside of the cell absorbs blue light and re-emits it at a longer wavelength, red. And so you get energy back, but it's shifted. And the direction is shifted because often the emission is relatively in all directions, depending. But if you change of that incident beam, suddenly it's much better than the coming from itself. So now we have to start thinking about color. If you have transfer of energy from one color to another, one wavelength to another. All right. So we're all going out to sea together. Some of us are on a ship, some of us are diving. I'm gonna be a diver. I scuba dive, you can put them on. All right. So let's imagine an ocean that has no particles. That's kind of no particles. No particles, but does have a pollution. And we're looking at a wavelength in which that pollution is occurring. So I want you to think about, for those of you who are on the boat, sailors, looking over the side. You can see. For those of you diving, you can fly. Take a moment and think. Remember the person next. Just really be free. Take purple chair. And also remember that. So, what do you think? What do you think the sailors see? let's just give me some ideas. There are no particles. There's no scattering to be direct. So it looks darker. That's somewhere that you just said. The question is, what about the interface? Right? What are your ideas on the interface?
I thought we would still have, only see light.
So if you look in the direction, so I'm looking at the glint off the floor from that window. And I can see glint, never want to see glint off the floor here, reflection. Okay, what if I look here? So the question is, if you look in the direction of the glint, depending upon, I did not define the properties, I didn't tell you. But you could make measurements that might remove it, so that the fact that I didn't tell you, you could decide, right? If you looked in the place where there should be glint and you didn't see it, that would tell you something about how I defined it. If it was in a place where there wasn't glint, you could just look at what's coming from it. Let's look here. Because we know we're going to see, we see glint, we see white, right? We see, okay. So let's look where there is no reflection. What do you see? Black. Because there's nothing to scatter the light back out of the silver. Look. Black. That would be so cool, wouldn't it? All right. Okay. See the diver? No, they don't scatter. Okay. What's the diver's?
Feel of light.
Yeah, like,
Stay.
yeah, I could see that. What if I've been down another 10 meters? Yeah, less light, right? Because it's getting absorbed. What if I looked here? Look back, right? So it depends on the angle at which you see it, right? If I looked this way, it looks black. Everywhere I look, it looks black. I look in B. And then B is just gonna get darker and darker and darker. So looking into the B, it looks like I couldn't do this and I couldn't do this very well with my advanced skills in PowerPoint. So if I look in this direction, it's gonna look black. If I look in this direction, it's gonna look black. If I look backwards, it's gonna look black. But if I look at the sun, the direction of the sun, I'll see the beam. Okay? Well, right? If you were just looking through a monochromatic light, you just follow, say, blue light, and it depends on the absorption. You had, if your eyes were your own white light detectors, RGB, the color would change depending upon the absorption properties. I haven't told you, I just said it was absorbing. And it's binary. But excellent question, because it changes, right? Following blue light, green light, red light. It's just water would be very different attenuation as well. Yeah, excellent. So do we have a natural analog? Of course, because otherwise I wouldn't have put this up. Okay, so here is a very cool image, again, from the NASA Outer Space Flight Center response team. For Motus, this is the Rio Negro in Amazon. It's an image taken from 2010. There's a scale bar, and you see this very black river combining with this very blue river. Okay. If we look at what that looks looks like this up. See very different aquifer patterns. And so this river is dominated by a dissolved absorber, called dissolved organic matter, better known as CDOM, which we spent a whole lab on. This part of the river is dominated by particles, synthetic particles. A whole lot of sessions scattering of particles. And when they meet, you can see like the most, I mean, so these are boats, right? These little white things are boats. So that's the scale of this new system. If you get up close, as the border, you could like literally put your hand in. And some of the rivers here, you put your hand into a river. There's not many particles in these rivers, but you can lose your fingertips. You can't see them because there's so much CDOM in the water that there's just no way left. Literally over centimeters. So it's fantastic. Okay. So now we're going to consider the ocean that doesn't have absorption. So don't pretend water is actually clear. It does have particles. Take a moment for yourself. Now prepare up. Take a moment to think about what we're going to see from the ship and what we're going to see from the diagram. Okay? No absorption. We're not losing any light. Okay. Moment to think yourself. Take a picture of your expressions. Fabulous. Use if you're going to pair up the booth, third table, 10 people, I want you to pair up this way. People behind you, and the three of you, each two. Got something? All right. So it's gonna see. What? Why white?
Because all of the other things.
And. Yeah, so we have that one in there. But I was getting at as long as it's kind of fast.
Yes, yeah.
Right.
That's good.
So maybe think about that. Right, but I didn't say. But it was.
Yeah.
So. Good interpretation. So that beam that comes down is going to be scattered, and what gets scattered back to your eye, it comes from a single back scatter. From multiple forward scattering. Or combination of all the above. Okay. And you can imagine it's then going to be like really complicated when you look at light that's coming out of the ocean. You want to say, oh, it's scattered off of one small particle. Or it's scattered many times off of many different sized particles, and how are we going to interpret that? Because it's very complicated. Okay. Make a lot of approximations. So keep that in mind when you think about modeling scattering. Okay. What is the diagram? So I think I have white. What is the diagram? Or what? You imagine what it's like swimming in a sea of apocalypse or a milk. Right? We can fill that with those moves again. That is. All right, the natural analog, or we could just wait to tomorrow morning when it's really foggy. Right, and when you're driving, you turn your brakes on and you blind yourself because there's so many water particles in the air and it's scattered. So that's a little. So you guys are because of your attraction. Perfect. That's a perfect way to approach the problem. And like, what am I experiencing in my life? And then you can say, what would that look like in the ocean? So that's the perfect way to begin to solve a problem. And often your intuition will help you. Sometimes it might not be perfect.
So next time we might have comments.
Beautiful. Everyone pulls their shades out like. Your sun is 4 hours. Another analog is working in ice. Working in sea ice. You can imagine we have a colleague, Scott Pegoff, who actually made measurements of gradients through a core of sea ice. Changing distribution of gradients as we go through a meter of sea ice. Paper, beautiful design of instruments. So all sorts of fun things. Or you could be an apocalyptophore balloon. So apocalyptophores are phytoplankton. They're small, couple microns. They have calcareous plates as their cell wall. That's chalk. Very bright scatter. And so from space, you can definitely see them from space. They look bright. There's absorption by water, so the light they scatter is blue. But you know, it can be pretty amazing. I think this is actually sediment. That might be sediments. I can't remember if that was sediments or that's apocalyptophores, but it's a small scatter. This is glacial flour. Coming from escalation, we move over to bedrock, they grind up the rock through particles, wash into nearby waters, creating scatters, really tiny scatters, and so you can get milky waters. This person is particularly happy. This escape cameraman person, really happy to be seeing this incredibly beautiful, highly scattering lake. Okay, so these examples are sort of artificial, but fun to think about. Fantasize about ocean objects, fun things to do. But what I want you to realize is that that is actually happening in the actual ocean. When we think about different wave bands, there are different wave bands at which the ocean is a pure absorber. And wave bands where it's essentially. And so if we can make measurements of the light coming from the ocean in really highly resolved wavelength bands, we can begin to simplify our radius. If it's a pure absorber, we can make more scattering. If it's a pure scatterer, we don't have the complication of absorption. And so just a little exercise we've just gone through is actually quite useful in thinking about satellites and what satellites do. So it's a pure absorber in the infrared, unless you're in like crazy scattering waters. It's close to a pure scatter in some parts of the spectrum, depending upon if you don't have a lot of seagull in the water. And so here's some pretty low resolution imagery. I think it's Lotus. I got this off of the Giovanni website, and I just took the radiance leaving the ocean atmospherically corrected at the 412 band for Lotus. And I colored it myself, remind myself. And so it's very bright offshore. And then as you enter into the Gulf of Maine, we're sitting about right here. No, actually, we're not sitting right here. It's going to get really dark. That's because we have a lot of absorption in the stuff coming out of the river. And when we get offshore the Gulf of Maine, it's very bright. Okay. If we go to the 555 channel, it looks like this. There are places where it looks black. That's really light, you know, it's pretty dark. And then if we go to the red, still like me. Way up here. I'm gonna go stand by it while I color it. Yeah, they have fun things. We have the largest tide in the world, it's a lot of right? By some of the rivers. But so essentially, we could find an analog within a channel. Help us. All right. My favorite image, Norway. Side of people in the Barents Sea. And you could write pieces on this image. And you could write pieces about scales of physical mesoscale variability, its impact on phytoplankton dynamics, right? It's like clearly some water is isolated hydrodynamic from other water in there. I don't know. Go look. You can look at the variations in color. Is that pigment? Is that concentration? Is there side distribution of the pigment? You literally could write pieces of concept. And Collin Roesler is one of my favorite photographers. He's from Hawaii. He in the studio when I was there. He just sits in the surf with a big camera. He gets pounded by waves. So his is in Hawaii. He's got this beautiful wave coming over the big wave. Here's another one that's changing color. Okay. More blue absorption going on there. This is now his son, who's now grown up, taking pictures of his dad, taking pictures of the waves. There. and balance light. Sentence. So go to his website, it's. All right, last thing. We were talking about the transfer equation. How did we get up here? Here's a beam. We have a beam coming in from the surface. And imagine you have a sensor. You can take that sensor, lower it down, make measurements as a function of depth. And so, gradient transfer equation is going to help you think about what's happening to the light along that path. So, take a moment to describe it, maybe sketch it, maybe schematic, graph equation, again, however you think. Like, what's going to happen to that beam of light as we measure it going deeper? Think about it. Pick one aspect of what you think is going to happen to light. Talk about it with your partner. Okay. Last time we're going to compare it. You compare it to the original part. So think of one optical process. Detect the light. What's going to happen is we measure it from one depth to the next. Give it your partners. How many people picked absorption? Talk about. How many people picked scattering? Talk about. How many people picked fluorescence? Oh. That's okay. All right. What do you think? Do you feel a little bit more like you know what can happen to gradients as it propagates in the ocean? Get all the fun exercises we did today? Or does it still feel like I couldn't remember to start? Or... So write down your answer. We didn't look at the radiative transfer equation. Did I tell you what it does though? It do. Describes how light changes. What impacts light as it propagates through the ocean? What impacts? You mean throw some terms out. What impacts light? Huh? Absorption. Okay. So we're going to lose some light from absorption. What else? Scatters, right? What's going to happen when light scatters off of a particle? Going in any direction, right? What happens if we have light? That's a changing color. So no, we did not talk about the radiation. Correct. Talk about anything that might help you think about it. All right. So there it is. You have gradients coming down. You don't need to write this down, just think about it. We're going to talk about this so much. I want you to traveling along a path. I made it complicated because it's at an angle relative to the vertical. But we're measuring it as a function of depth. So the processes that impact the beam, we talked about absorption. So what's that going to make my arrow look like? It just moves like the energy. Bigger arrow, smaller arrow. How would you demonstrate? Smaller arrow. Would you make that arrow shorter? Would you make it thinner? Yeah, I can make it thinner. I made it shorter. We'll just make it thinner. Depends on how you sketch, right? So it's going to be the same arrow. It's just going to be thinner. Okay? Depends on how you sketch. How you scattering out of the beam. How am I going to sketch that? Yeah, whatever. Get it out of the beam columns. Get it out. So do we got to do that anymore? No. Because we're measuring light. Whoa. Measuring the light going in that direction. We're looking in that direction, right? So we don't see that light hitting us in the back. What about scattering in the beam? You could have light from some other direction scattering in the direction you're looking. Darn that scattering. We can have inelastic scattering, which is fluorescence, going from one wavelength to another. Purple and blue. And then we end up down here with the light. And we have to figure out all of these processes based upon method of light. So the first thing we have to do is say, all right, we're looking at radiance at a function of the angle that we're looking along some path. So this is the length of our path. That's R. But we're measuring it as a function of depth, right? So we have to take into account that angle, do some geometry, and figure out that the depth is related to that distance of the slanted path. We know the angle and take the cosine of it. So we could be looking at the change in radiance with depth. And then we use absorption. So I can absorption. But literally, the absorption coefficient times the radiance is how much we've lost. The scattering times the radiance is how much we've lost. Not so bad, right? Scattering going in, not so great, right? We have to take into account all the light coming in all the directions, scattered by something that describes the scattering angle out of that light. So this describes the angular distribution of the particle scattering, and this describes the radiance from some other angle. It's really complicated, but it's just now. But that'll tell us how much of this light ends up in our path. Cool. And then the inelastic scattering, I didn't even put it down. It's just a transformation of light that's absorbed into some other wavelength. It's also got an angular distribution. That's another term. There you go. We lose light, we gain light, we transfer light from one wavelength to another. So we're going to spend the next 4 weeks taking apart little pieces of this. Okay. All right. So wait one after 11, and we don't have anything until lunch and lab, right? Back at noon. Go and dry. I see a little bit of sun out there. Just get outside. Go sit out there. Meet each other.